Okay, so logarithms are a way to find an exponent that we don't know. And sometimes they're just overkill. Like for that, this is like, I've got a bunch of 2's, I got to get to 32, how many? And you could write, well, the log of 2, log base 2 of 32 gives me my exponent. You could like throw it in your calculator or ask a friend. But that's overkill, right? Because you can just go 2, 4, 8, 16, 32, 5 of them. So sometimes like you don't need to switch it into log form. It's a tool. It doesn't need to be a crutch. This though, you got 3's, multiplying 3's together, bunches of them. How many do I need to get 8? Well, 3 times 3, 9. So right there we're over. So it's not going to be something that you're like a number, a decimal that your brain can do. So it'll be between 1 and 2 because if you go 3 squared, now you're over. So this you'd leave as log base 3 of 8 is that number. What actual decimal that is it? Nobody cares, right? Throw it in your calculator, you get some awful decimal. Did you get it?
Yeah.
Is it like 1.4? 1.8. 8, 9. All right. Right? There's no reason your brain should do that. All right? You probably should be able to guess that it's between 1 and 2. But you can leave that. So sometimes like you just throw it into logs and leave it. And sometimes you need a little of both. You need to like throw into logs and then process what's happening. And so this one's gnarly and I want to walk through it with you. Yeah, okay, so let's squeeze that over. I'll tell you about that in a second. That's gross because there's 2 different bases. If this is a calculated problem, so much easier to graph one of them. It goes like this, and then graph the other, and goes like this, and you find where they hit each other, right? So like that should be your go-to. If you have a calculator, like just blast it with your calculator. But if not, then we have to do some fussy business. And one of those, if we need an expression, eventually I want this to say x equals something, right? And so I need to start ripping the x's out of there. The only way that I know how to do that is with logarithms, right? So focus on either side. It doesn't really matter. But I might focus on this side and turn this into log base 2. You could focus on the other side and make it log base 3. It'll all come out in the wash, but that's the first thing I see, and it's a smaller base. I'm going to use that. And I want to raise to some, I want to figure out what power should be the power, and this whole thing is my result. Ugh. First. Again, we're trying to, like, the goal is to extract the x's. So I'm kind of happy about this one, this x plus 2. But this is still stuck in there. Any ideas about how you can pull that out of there? What do you think?
Go to the left and then you could divide the other side by.
Yeah, right. You can pull this out as an exponent, right? So you can pull this whole thing out like as if it was a 5 or something, right? So you go pull it out like that, and it's whatever the exponent is times log base 2 of 3. Groovy. I kind of want to divide like you suggested, and if we do that, you end up with this. That's a little bit obnoxious because now I've got like 2 sets of these, like they've got more x's, and so I'm just kind of visually working about what I would do if I was obliged to do that. This would become x over x plus 4. Don't write this down, and it would also become 2 over x plus 4. And now I've got 3 sets of x's. It's going the wrong way, right? I'm getting more x's, right? It's kind of like, I don't know, gerbils that keep multiplying and you try to make them stop multiplying. So I might try, instead of multiplying that x plus 4, or dividing that x plus 4 out, I might try a different tactic. And that's not a failure that you tried that and said like, hey, try this. And sometimes I'll do that and like go down this route, and then eventually you see it not going the way you want. You're like, more X's. I want fewer X's, and you just backtrack. That's why you keep a record. So maybe instead of that, what I might do is distribute. This is just some nasty decimal. Let's just distribute it in. You end up with x log 2 of 3 plus 4 of those log 2 of 3s. And this x plus 2 is still waiting patiently on this side. Like, hi, I'm minding my own business. What's nice about that is this piece is just a number, and that's a number. So let's kick all our numbers to one side, kick all our x's to the other. So push all the x's that way, maybe. So this is, I have like 1.6 x's, right? That's log base 2 of 3. I'm going to subtract that x off of this side. Here's a positive 2. Let's subtract whatever gross number this is off of that side. Not pretty, but it's better than it was before because I've got all the x's on one side. What can you do with that now? Yeah, pull out an x by factoring, and what we're left with on this side is gross, but just numbers. This side is also gross, but just numbers. And therefore, the x is sitting there. We consolidated the x into one part packet. We can divide both sides by that log base 2 of 3 minus 1 into our x. Holy gross, right? That's awful. This looks awful. But we did it, right? We consolidated all of these x's and put them into one spot, and we got just numbers over there. And if you had a calculator, you could find that decimal. But if we had a calculator, just to start with, you'd graph it and find the intercept. Like, so often they'll leave this as a value, that an unevaluated number, just because they want to see you play the game with all of these. See if you can visualize how to extract the x. One of the issues with that is gross looking. In the solutions, they'll often leave something like that. Sometimes they'll take this and use a change of base formula and give you a different version of it. It's the exact same decimal. And so as you're doing these, to check if you're right, do throw this in the calculator and get some gnarly decimal and check their answer and see if you get the same gnarly decimal. And if you got it, I don't really care what format that's in, as long as the x's are all on one side. Right? Once we see change of base tomorrow or whenever I see you next, you can see how they would convert this into the other format that they leave. But unless they ask you specifically to leave it in one form or another, leave it like that. That's horrible. And check it with the decimal. Now, if you left it as a decimal, you might as well just have thrown it into your calculator to begin with. Does that kind of make sense? Just like verify that way. Cool. So there's one gross trick. The other tricks you're already pretty good with, and I've seen you start doing this already. One thing that I wanted to highlight was this part. You've started with already things like this. This is really e to the x squared minus 2 sets of e to the x. Is that okay? Maybe instead of e to the x squared, I might write it just twice, just to illustrate something. So e to the 2x is e to the x squared. Here are 2 of them, and here's 2 e to the x, which is really added together. it's really tempting to just be like, e to the x's on both sides, and maybe like just like extra scribble just to get them out of there. That feels really cathartic. And if you do that, then you're left with this solution that e to the x equals 2. And therefore, if you spun this around, you'd say I have log base e of 2 equals x. And so that's the solution for it, right? Is x equals natural log of 2, or ln 2 if you're into that nomenclature. There's an issue with this, though. And I think a couple of you saw this in your last homework stuff. What's the problem with blasting both sides out like that, dividing both sides by the same thing? Yeah, you lose a potential solution. Let me show you how that might look. Right? We resist temptation to just smack the a to the x out of there. If we pull this whole thing to the other side, you end up with e to the x times itself minus 2 e to the x's equals 0. This is a little bit of a safer bet because if you can then factor, think about it as one big parenthesis, and factor an e to the x out. So pull this out, You're left with that e to the x out front of your parenthesis, and you're left with the e to the x minus 2 inside. And therefore we have like two chunks that are multiplied together to get 0. This is the zero product property, which means like if this piece times that piece equals 0, either that one's 0 or that one's 0. We already saw that this one is potentially 0, e to the x minus 2. We did that when we first like scratched this and scratched that. We got e to the x equals 2. So you still get e to the x equals 2 like we had before, and so you still get x's natural log of 2. But this is where you can kind of see a little bit easier that also this is a potential solution, that this one, e to the x equals 0. Now, that one won't work very well because like I can't take a positive number 2.7, multiply it by a bunch of by itself a bunch of times and get 0. So this doesn't have a solution in this case. But often if you cancel something out like that, it is the case that it could have been 0. And if you pull everything to one side and factor, it'll become apparent that it's a solution. And so you can play that same game with this. Now this won't have the same issue, but this is e to the x squared minus 5, e to the x is plus 6. And I think you've done a couple of these already, where you factor something that is an exponential but really has a quadratic buried in there. Probably should have done it backwards. When everything gets pretty messy and I'm tight for time and short on mental bandwidth, I'll just switch out the e to the x for an m for a second. Whatever flavor variable you like. And sometimes that helps me factor faster. It's up to you. Often I'll write let m equal e to the x. And then we can factor it into m and what, 2 and 3. Oh, thanks. 2 and 3. That's not 2 and 3 and negatives. I'm happy about the negatives because this wasn't m, this was e to the x. And e to the x. And if two chunks multiply to 0, well then either one equals 0 or the other equals 0 or both. And so then you can kick the 3 to the other side and switch it to log form, natural log of 3. Right? What number is it? Don't care. Same thing here. End up with e to the x minus 2 equals 0. And so end up with e to the x equals 2. So natural log of 2. Now, you can kind of go on blind faith with these, but it's worthwhile just thinking about could the solution be true, especially if you had something like if this was a plus, this would be a plus, this would be a minus, and you're saying how many positive 2.7s do I multiply to get to -2? This might not have a solution, right? Cool. You kind of messed with those before. All right. And for my last trick. Kaboom! Sometimes things are not able to be solved by hand in a nice format, or maybe they're on a calculator paper and it's not worthwhile. I want you to be comfortable throwing two things into the y equals and seeing where they intersect each other. So try that with this one. I've got two functions, this one and that one. Chuck them in, see if you can find the two intersection spots. I'll show you on mine in a second. So I threw my two equations into y1, y2, and I hit graph, and I was just fortunate that this happens to be in a spot that I can kind of see the intersections. It's nice. If it isn't in a nice spot, sometimes I'll first try zoom standard, zoom 6, which gives me a 10 by 10 by 10 by 10. It kind of squares it up. Sometimes, if it's still not there, I'll try zoom fit, which is 10 or something like that. There you go. Your calculator kind of guesses at what you want to see. It thinks you want to see intersections, intercepts, and so it's guessing at what I want. But it doesn't know what I want. I barely know what I want. So sometimes you have to drive it yourself, right? And in this case, it was pretty straightforward, zoom 6. Great, we got that, and then we find our intersections with the second calc. We want an intersection of 5, and then if the first curve means it's on the blue curve, we say, yeah, that's close enough. Second curve means it's on the red curve. And we don't really even need to move it back and forth. Just fortuitously, it's in the right spot. So 0, -2, great. And then we have to run it again to find the second one, right? 5. Now we have to kind of cruise it up here. Still on the blue curve. So you get yes. Second curve, close enough. Yes, close enough. There we go. Cool. So it was 0 and 1 point. What is it? I can't see with my old eyes. There we go. 1.09. Neat. I hope that, I know that it's annoying to pull out your calculator and do that, but I want it to become just like a mainstream, easy thing to do. Yeah? All right. Then. That's all the tricks. The exponential equations is our next piece of this, so the time is yours. I'll bounce around and give you a hand.